So today's lecture is backpropagation algorithm. This is something which I wanted to introduce in the last class. Okay, again towards the end of the last class we had just started giving the ideas about the backpropagation, because major part of the last class was actually spent in discussing the concluding part related to the single layer perceptron, and then we had introduced the multi-layer perceptron, where the basic algorithm in which the multi-layer perceptrons operate is the backpropagation algorithm. So, I mean, whatever we had introduced in the last class, let me just write down those equations without much of explanation, because I think that those are pretty simple. So, what we took was the jth neuron. Take any neuron, okay, of the system, and let us say that we take the output neuron only. We take any one of the neurons from the output layer, and let's say that we take the neuron J, okay, and at the iteration number n. So, what we had written down are the error term, that is E of j at the iteration n is equal to djn minus yjn, where djn is the desired output at the jth neuron, yjn is the actual output, and this let us call it as equation number 1. Then we had defined the instantaneous value of the error energy En, error energy at the iteration n, to be equal to half of summation E j square, yes, n, and we varied n from 1 to, I mean, how many neurons there, yes, I mean this is j, indexed as j. So, j belonging to the set C, which includes all the neurons in the output layer. So, this was our equation number 2, and then we had defined the average square error energy E av n to be 1 upon n summation n equal to 1 to capital N E n, where what is capital N? Capital N is the number of patterns that we are presenting, okay, total number of iterations, because what we are doing is that with every pattern presentation we have been calculating these EJs, and consequently the ENs will be calculated as the summation of all these squared terms, okay, and E average will be the average over all these ENs, okay, I mean all these N's. So, this we call as equation number 3, which is the average squared energy. Okay. Now, we can write down the induced local field at the input of the neuron J. So, we are taking the neuron J, and at the input of the neuron J, okay, if we are taking the activation function, okay, the input to the activation function, because what we are doing is that we are summing up all the weighted summations we are calculating, and those weighted summations will be actually will be modified by the phi function. So, phi as an argument of Vj. So, where Vj is called as the induced local field. So, we are calling Vj as the induced local field, where Vj of n we can write down as what? As the summation of Wji, okay, right, Wji at the iteration n times Yin, where Yi belongs to which layer? The layer which is previous to it, yes, I mean previous to it. So, if we are taking the output layer, I mean J as any output layer neuron, then obviously it refers to the hidden layer that just precedes the output layer, okay, and we have to sum it up for I is equal to 0 to m, where m is the number of neurons in the previous layers, okay. So, this we are calling as equation number 4, and the actual output Yj of n, that is to be written as what? The phi function of activation function of Vj, that is correct, activation function of Vjn, and this is equation number 5, right. So these are the 5 basic equations with which we begin our analysis. In fact, what follows is a very straightforward mathematical treatment, okay, and we are going to calculate the derivative, the partial derivative of dou En dou Wji with respect to n, okay. Why? Because the change of weight, okay, that is delta Wji that we are applying to the synaptic weight. So delta Wjin is applied to the current weight, that is Wjin, okay, and this delta Wji that we are going to get is proportional to this dou En dou Wjin, right. So this we can write down as dou En dou Wjin if I have to calculate, okay. Let us again go back to this expression. Let us understand that where are we going to calculate this. If we are getting this, so we will have to apply it to the equation 2 very directly, okay. But in equation 2 we find that everything is written in terms of Ej square, whereas we would like to get the derivative in terms of Wji, okay. So there lies a bit of a problem. Actually, we could have substituted, I mean what we have to do is to substitute Ejn from this equation number 1, where it is to be expressed in terms of dj and yj, and again yj will be expressed as vj, and vj is expressed as wji, and then only we can and then only we can differentiate with respect to wji. So little bit of cumbersome. I mean, if we try to substitute this form of Ej and then substitute everything using these equations, okay, I mean it will be mathematically very much cumbersome. So instead of doing that, what we will be doing is just to apply the chain rule of differentiation. Simply because here in equation number 2, En is written in terms of Ej of n, alright. The best thing will be is that if we first calculate dou En with respect to dou Ej, okay, that we can very simply calculate from equation number 2, in which case we have to multiply this partial derivative by dou Ej dou Wjin. Again note that there is no direct relationship between dou Ej and dou Wji, okay. So we can only calculate dou Ej dou Yj, okay. So if we write down this term dou Ej dou Yj as the second expression in the chain rule of differentiation, then we can calculate that very easily. In fact, it is going to be minus 1 simply. In that case, we have to follow it up with a dou Yj, and that expression we have to have with respect to Vj, where we will be getting the term as phi dash Vj of n, where phi dash is the derivative of Vj of n with respect to, I mean derivative of phi Vjn with respect to Vjn. And then again we have to take the last term as dou Vjn with respect to dou Wjin. So that will complete my chain rule of differentiation. So we have to write ultimately this thing as dou En dou Ej, that is what we agreed for the first term in the chain rule. The second product term in the chain rule should be dou Ejn with respect to dou Yjn. The third term should be dou Yjn with respect to dou Vjn, and the last term in the chain should be dou Vjn dou Wji. Yes. So this simple expression is being written as a product of 4 terms, but getting the product of these 4 terms is very easy, because what we can simply get is dou En dou Ej of n we get very easily. What is that? Dou En dou Ejn, it is simply equal to Ej, yes, Ejn. So this is equal to Ej of n, very correct, okay. And what is dou Ejn dou Yjn? That is very correct, simple. Dou Vj dou Yjn, so simply take the derivative. Dj is dj is not varying with respect to Yj, so dou Ej dou Yj is simply be equal to minus 1. Okay. Then what other terms are required? So this term is computed, second term is computed, the third term is dou Yjn dou Vjn, and what is that? That is simply equal to phi dash. Okay. We can exactly compute it only when we know the activation function. Okay. So typically we need a activation function, okay, in order to exactly calculate this, but in general, given any phi, we can express it in terms of phi dash, where phi dash is the partial derivative of the phi function with respect to the activation input, that is Vj. So this is also expressed, and the last term that we are having is dou Vjn dou Wjin, and what is that? That is simply equal to Yi of n. This is simply using the equation number 4. Followed? So these are the 4 expressions that we compute. Alright. So that means to say that now this dou En dou Wjin is expressible in a very manageable form. This term is very nice, minus 1. This term is Ej. So it is minus Ej phi dash Vjn Yin, simply dou En dou Wji. So we can express it as follows: dou En dou Wjin is equal to minus Ejn phi dash Vjn Yin. Okay. And now the correction delta Wjin, which is applied to Wjin, that can be written as, because delta Wjin is going to be proportional to dou E dou Wji, isn't it? Okay, error with respect to Ji. So what is that constant of proportionality? Eta. So it's equal to minus eta of dou En dou Wjin, because it should be in the direction negative to the direction of the gradient. So that means to say that it is simply becoming equal to eta product this term, okay, eta product Ejn phi dash Vjn times Yin. And now what we are going to call this term, you see, this term is nothing but the error multiplied by the derivative of the activation function. Okay. This term we are expressing, we are substituting another term delta of j, because everything is here indexed with respect to j. So delta j at iteration n replaces this product term. Okay. So we define delta j this way. Okay. Actually delta j we originally defined like this, that delta jn will be defined as the derivative of this error energy, that is dou En with respect to dou Vj of n. That means to say what? That the derivative of the error with respect to the activation input, okay, which is nothing but the, which is this term dou j that we are going, delta j that we are going to write. So this in fact could be expressed as minus dou En dou Vj. So we could express it as dou En dou Ej n times dou Ejn with respect to dou Yjn with then dou Yjn dou Vjn, and this whole thing ultimately boils down to nothing but Ejn phi dash Vjn, right. So this is an important expression. So this is delta j, I will write it down in the next page. Okay. So, this will be equal to delta Jn equal to Ejn phi dash Vjn. So, this is our equation number, I should call it as 6 because we have already gone up to 5. So, this is going to be our equation number 6. Okay. So, what is the significance of this delta J term? What is the physical significance of this delta J term? This delta J term is nothing but the derivative of the error with respect to Vj, that is to say its own induced field. Vj is its own induced field, and this is nothing but the gradient, and this is the gradient with respect to the induced field, and this is a gradient that is very much local to that of J. So, we are going to call this term, that is delta J, as the local gradient, Okay. So, with respect to the local gradient, we can express the change of weight that takes place, that is delta Wjin is equal to eta, the learning rate, times delta Jn, that is the local gradient, times Yin, which is the input. So, you see, I mean, this is a very interesting equation that we have got, that is delta Wjin, the change of weight, equal to the learning rate times the gradient, the local gradient, times the input to that, okay, input to the neuron J, which is in the form of Yin. So, if since Yin will be known, eta is a given learning rate, what we have to get is the local gradient. Now, the most important thing is that how to compute this local gradient. Now, local gradient computation is very easy as long as we have the neuron J as the output neuron. Actually, our analysis began with that. We began with the neuron J to be the output neuron, and given that neuron J is the output neuron, this is what we get as the delta J, that is error times derivative of the activation function, which we know. Okay. Error is easy to calculate because we will be feeding the desired, we will be feeding the training pattern where we will be giving the desired output, dg of n will be known to us. We will be obtaining the yjn from the network. So, calculating ejn is not a problem, and we know that what kind of activation function are we using. So, we just have to take the derivative of that activation function, and then we can calculate the local gradient. So, calculating the local gradient for the output neuron is not a problem. Okay. It is quite easy. But now, if you ask me that how to calculate such kind of a local gradient for the hidden neuron, that is where we have to do some more extra analysis, right? Because if it is hidden neuron, then you don't know EJN, do you? You don't know it because EJN you are not supplied with the desired output for any hidden neuron, because hidden neuron is not having any desired output like thing. So, you will have to calculate that what this you will have to calculate this delta J in some other manner, and that is what we are going to show in our analysis that is going to follow. Now, depending upon the location of this neuron J, so two cases can arise, okay, that is neuron J is the output neuron, is belongs to the output layer, in which case delta Jn can be easily calculated from 6. And case 2 we consider where neuron J belongs to a hidden layer. And there lies the problem. There we have to calculate something which is equivalent of this delta G, okay, in the hidden layer. So we will have to break our analysis further. So now the model that we are going to consider, okay, will be as follows. Let us consider that there is an output layer, okay, there is a hidden layer, and then there is a layer that is previous to that hidden layer also, okay. Simplest case is that if it is a 3-layer architecture, okay, where we will be having the input layer followed by the hidden layer followed by ultimately the output layer, okay. So we consider, and let us just take a typical signal flow graph for that. So we consider the neuron J to be in the hidden layer. So hidden layer means it is getting its input from a layer previous to it, right. So let us consider that. So let us say that this is where the neuron J is there. So here we were having Vj of n, the local induced field Vj of n, which will be the summation of all these Wji times the inputs, okay. So here we will be having y0, that is to say the bias, which is equal to +1 over here, and the weight, that is Wj0 is equal to Bj of n, which is nothing but the bias term. And then we will be having all the other y's. So we will be having y1 over here, the first input, and this we will be writing as Wj1, okay. And like that we will be having some yi, okay, everything we will be writing as y1 of n, and here yi of n, that is how we are going to write it. And here the weight, corresponding weight will be shown as wji, again wj1 at iteration n, wji at iteration n. So everywhere we should not be omitting this n, okay. And there will be many others, okay, to follow. And in fact, mind you that these y's, that is to say the input that is coming from the previous layer, is not only connected to this hidden neuron, but all the other hidden layer neurons which are there in the same layer, right. I mean, there will be some other neuron here, some other neuron here. So typically we should consider the y connections like this. So this is the way whereby we indicate in the graph that it is connected to several other neurons in the next layer, okay. So all these y inputs are connected to the neurons in the succeeding layer, right. So these are all our y inputs, and we calculate Vjn, which is the induced local field to this neuron J, which is in the hidden layer, right. And then this Vjn, I mean on this Vjn we will apply the activation function, phi function, and then we are getting what? We are getting yjn as the output, right. That is what we are calling yjn is equal to phi of Vjn, okay. Now this yjn will be connected to the output layer, right. To all the neurons in the output layer it will be connected, right. But we are considering, I mean as a specimen case, we are considering a single neuron from the output layer. I mean as a detailed connection we will be showing that, and let us call that neuron to be the kth neuron, so that here we are going to compute Vk at iteration n, where k belongs to the output layer, right. So k belongs to the output layer here, and yjn will be connected to several other neurons in the output layer, I mean to all the neurons which are existing in the output layer. So that is why we are showing the connection like this. And here what will be this weight? This will be Wkg, this will be Wkj, where it connects this output neuron K with the preceding neuron J, which belongs to the hidden layer, right? Yes, very correct. WKJN. Everywhere we will be having N because it is analyzed with respect to the pattern number N. Now, likewise this VKN will be connected to other neurons which are there in the preceding layer. So, this is, I mean, I can say that this happens to be the hidden layer, and then coming to here, this happens to be the output layer. So, here what we are going to get is that there will be several other inputs to this VK, right, starting with the bias, that is +1 over here, and then there will be a WK0N or okay, and then there will be other inputs, I mean, or other outputs of the hidden layers which will be there. So, everything will be connected to the output layer. So, like that it will get connected. So, this is the way our graph would look like. So, here all these inputs are coming from the hidden layer, right, and K belongs to the output layer, okay, and then on this VK we will apply again another phi function of that, and in the process we will be getting Yk of n. So, Yk of n will be the actual output, right, at the neuron K in the output, right, and likewise there will be a desired output which will be dk at iteration n. Okay, so, dkn will come here and Ykn will also come with a minus sign. So, dk minus Yk, and that will give rise to our Ek of n. Okay. So, this will complete the whole signal flow graph. Okay. So, this is a signal flow graph, we can say, considering J as hidden layer neuron and K as output neuron. Anybody having any doubts or confusions related to this signal flow graph? Is it understood? Let me just repeat once again in a nutshell. We consider neuron J in the hidden layer that is connected to its preceding layer. So, all these Y's that we have shown are the outputs of the preceding layer being applied on this Jth neuron. We compute Vjn, we then compute Yjn from it by going to the activation function, and then all the hidden layer outputs will be connected to the neurons in the output layer. We take a typical output layer neuron, kth output layer neuron, and then we connect that to all the hidden layer neurons over here, then operate this Vk with the phi function, get the Yk, and we can compute this Ekn. Okay. So, this is the complete signal flow graph that we are getting, right. Now, we can compute the delta J. Okay. Delta J is what? Delta J is going to be the local gradient for the Jth neuron. Now, this time the Jth neuron is in the hidden layer, right. So, delta J actually according to the very basic definition should be written as dou En dou Vjn. Okay. That is the definition of the delta J that we have been considering. Okay. So, that we, instead of expressing that directly, we can express it as dou En dou Yjn, okay, multiplied by dou yjn with respect to dou vjn, and that is what? That is the derivative of the activation function of jth neuron. So, this should be phi dash j vjn. Is that understood? So, this is our equation number, what is the equation number running? 7. We have to give equation number 7 to it. Okay. So, this is understood. So, this is again by applying a simple chain rule, that instead of taking the derivative with respect to Vj, we are first taking the derivative with respect to Yj and then taking the derivative of this function with respect to Vj. Okay. So, that is it. So, now we have to calculate this dou En, dou Yjn. Now, is it very easy? Let us see that. Firstly, that the En expression, what is the En expression now? Half of summation Ej square. Are you very sure about it? Divided how? Some people are saying Ek square, some people are saying Ej square. Ek square, because K belongs to the output layer, and when it comes to the question of error energy, the errors are all computed at the output, because that is where we can only compute the, this output is only available out here. So, whatever Ek we can calculate, that is only at the output layer, and we have been using J to be the hidden layer and K to be the index for the output layer. So, we should write Ek square in where K belongs to the set C, where C is a set containing the output neurons. Okay. So, here, so this one we are going to call as equation number 8. So, now with that idea, let us try to compute dou En, dou Yjn. Okay. Now, this could be calculated as follows, that we can simply write it, actually this we can first differentiate with respect to Ek, okay, and then Ek can be differentiated with respect to Yj, and that we have to sum up over all the K's, isn't it? Take any one Ek, taking any one Ek would give you Ek multiplied by dou Ek dou Yj, right? So, we are summing it up over all the neurons in the output layer. So, this is summation over Ekn dou Ekn dou Yjn. Is that correct? So, this one now again dou Ek dou Yj is still not very easy, because K belongs to the output and J belongs to the hidden. So, we have to do some further mathematical manipulation. So, let us carry on. So, we can express it as Ekn, summation Ekn dou Ek with respect to dou Vk. This we can calculate, should, isn't it? Can we? Because everything is pertaining to K only, and then what remains is dou Vkn dou Yjn. Should it be easy or difficult? Should not be very difficult. Look at the diagram out here. Okay. You see Yk, ultimately what we are doing is that Vk we are getting. Now, Vk will be nothing but expressible as the summation of Yj Wkj, right? So, this should be computable. So, we should be able to compute this. We should be able to compute dou Ek dou Vk very easily, okay, and then we will be in a position to calculate dou E dou Yj, and if we calculate dou E dou Yj, we will go back to equation number 7 and we will be calculating delta J. And what is delta J? Delta J is nothing but the local gradient of the hidden layer neuron J, and if we can calculate delta J for the hidden layer, then simply we will be applying this rule again in order to adjust the weight between jth hidden layer neuron with its preceding ith neuron in the previous layer. Okay. So, that means to say that we will be then in a position to adjust the weights prior to this also, because you see, if we look at this diagram, what we can do is that we will be in a very easy situation. I mean, we will be I mean it will be quite convenient for us to calculate all this change of weights in the output layer. Okay. And then we will go back and we will be calculating all these change of weights which are happening in the layer previous to it. Okay. So, just simply what we have to do is to extend this mathematical analysis. So, we have to now concentrate on this dou Ek dou Vk computation and dou Vk dou Yj computation. If we can do that, okay, let us call this as equation number 9, that is dou En dou Yjn equal to this. So, if we can compute all the components of equation number 9, okay, then we will be in an easy situation to compute the local gradient of the hidden layer neuron, right. So, let us see that dou Ek dou Vk is going to be very easy. Why? Because Ekn is simply equal to what? Dkn minus Ykn, and Ykn is nothing but phi of Vkn, right. So, what is dou Ekn dou Vkn? That is equal to minus phi dash. In fact, we should write phi dash of k. Okay. Anyway, phi dash of Vkn. Yes. Okay. So, this one we call as let's call this one as equation number 10. Okay. And this one as equation number 11. Okay. Now, for neuron K, the induced local field can be written as Vkn equal to summation j equal to 0 to m Wkjn Yjn. What is m in this case? Number of hidden layer neurons. Okay, means Vk, I assume, is connected to m number of neurons to its preceding layer. Okay. So, that means to say that there are m number of neurons in the hidden layer just preceding to the output layer. So, this is expressed as j is equal to 0 to m. 0, I mean there are m number of hidden layer neurons only, but j is equal to 0 case is for the bias, right. So, this is equal to Vkn is equal to summation of this, which should be our equation number 12. So, from this it is easy to calculate dou Vk dou Yjn, and what is that? That is equal to Wkj of n. Very good. So, this is our equation number 13, right. So, have we got what we were wanting? I think so. We have got dou Ek dou Vk, we have got dou Vk dou Yj. That is what we were wanting, isn't it? Dou Ek dou Vk and dou Vk dou Yj. These two terms we wanted. So, now that we know that very well, dou Ek dou Vk being equal to minus phi dash of Vkj and dou Vk dou Yj being equal to Wkj, simply we can express now dou En dou Yjn, that is equation number 9 can now be rewritten as. So, I can do this. Equation 9 may be rewritten as dou En dou Yjn, which is equal to minus of the summation of Ekn phi dash Vkn Wkj of n. Alright. just tell me that what is this minus of Ek phi dash Vkn delta k. Okay. So this is equal to, no, this Ek phi dash term is equal to delta k. So this is equal to minus of delta kn times Wkjn, and I have to sum it up over k. Okay. So this is interesting. So we have got the dou E dou Yj, okay, and in this case we have made use of the fact that delta Kn is equal to Ekn into phi dash Vkn, going by our original definition. In fact, we had possibly numbered that also. Yes, that is as per equation number 6. As per equation number 6, we have expressed this as follows. Okay. So now we go back to the expression involving delta J. All right. We now want to compute delta J. So delta J is, yeah, equation number 7. So we have to go back to equation number 7. Okay. So applying the above on equation 7, we get what? We get delta J. In fact, we should write delta Jn itself, that is equal to phi dash of j into Vjn, the term that is already existing with us, phi dash j Vjn, okay, and we have made dou En dou Yjn, right. So dou En dou Yjn is simply this. So simply this expression. So since we already had a minus over here, and this one is also giving us this dou En dou Yjn is giving us another minus sign. So together it will be of positive sign, summation of delta Kn Wkjn, and this we have to sum up over k. So we have got one very interesting expression whereby we are expressing the local gradient of the hidden layer neuron in terms of the local gradients of the output layer neurons. Okay. In fact, it is nothing but the weighted sum of all the local gradients of the output neurons to which it is connected, because here summation over k means what? Summation over k means that this j is connected to all the k's in the output layer. Okay. So here what we are meaning is that all the k's, I mean, since we are summing it out over all the k's, that means to say that whatever local gradients we have at the outputs, we are considering the summation of that, weighted summations over all that, okay, and then we are multiplying it by the derivative of the activation function of itself, that is phi dash j means it is the derivative of the activation function of the jth neuron, and then only we are getting delta j. So to compute delta j, okay, the signal flow that we are getting is very interesting. Let's see. You see that what we are doing, we are calculating all these deltas. Deltas are nothing but E times phi dash, isn't it? Deltas are nothing but E times phi dash according to our definition, E times phi dash. So what we can simply show is that, let's say that we have got number of output neurons are there. Let's say that we have ml as the number of output neurons. So what we are showing is that here we are showing all the errors. Let us say that this is E1, okay, this is error E2, this is error EK, everything at the nth iteration. Finally, this is our EK, EMLN. Okay. So, for every output neuron, we can calculate the error terms, isn't it? And then, if we multiply the errors by their respective activation function derivatives, okay, in that case, what we are trying to do, this EK is, these E's are available to us, and we are multiplying that by E1 is available in this case. So, E1 will be multiplied by phi dash 1 V1n, phi dash 1 V1n, okay. And what will I get as this term? Delta 1n, okay, like that E2, like that EKN. So, here when EKN is the error term, and we are multiplying it by phi k dash VKN, okay. Here what are we getting as delta Kn, okay, and the last term will be here phi dash ml VKN, or here VMLN, okay, and here we are getting delta MLN. So, all these deltas are available now. Now, what we are doing, again go back to this equation, study this equation. What should we number this? We should give the number as what's the running number? What was the last number that we have given? 13, 14, equation 14 we say. Okay. So, then what we can do is that all these things we have to add up, multiply by the, no, this delta k's we have got, they have to be multiplied by WKJs, they have to be multiplied by WKJs. So, what we are doing, that the first term will be multiplied by W1J, the kth will be multiplied by WKJ, and the mlth term will be multiplied by WMLJ. Alright, and this together will give me what? This together will give me delta J of, no, they are not. So, this is simply summing it up, okay, and then this summed term we have to go through what? Phi dash J Vj of n, right, and that will give me delta Jn, right, and here we should indicate the signal directions also. We are first starting with the error terms, multiplying the errors with their derivatives, with the derivatives of the activation functions, getting all the local gradients, multiplying the local gradients by the synaptic weights from the jth neuron to all the output neurons, okay. So, synaptic weights we are doing the multiplication, getting the sum of all these weighted sums, I mean that is to say sum of delta k WKJs, and then on this summation we operate the phi dash term, and then we are getting the delta J, which is the local gradient of the jth neuron, right. And once we get the local gradient of the jth neuron, the calculation of the weight correction is pretty simple. In that case, what we simply have to do is, like the way we had applied, you remember, simply this equation we should reapply, okay. So, where delta Wji will be the change of the weight that we are doing between the jth neuron and the ith. Ith is connected to the layer previous to the hidden. Okay. So, delta Wjin will be equal to eta times this delta Jn, okay, but this delta Jn is going to be the local gradient of the jth neuron times Yin, and Yin is the input, is the ith input to the hidden layer neuron J, right. So, this basically completes our analysis on the back propagation algorithm. In fact, this is in a nutshell what the back propagation algorithm looks like. You see, all the mathematics that we have done, in fact they are all very simple mathematics, because the only great thing that we have done is taking the derivative, and that too instead of taking complicated derivatives, what we have done is simply to conveniently apply our chain rules so that the derivative expressions become as simple as possible. And after doing all that, what results is that you start with the errors, multiply the errors with the activations, get the gradients, multiply all the individual gradients with the synaptic weights, get the gradient of the preceding layer. And this time J is just directly connected to the output. But what happens if J is sandwiched between another hidden layer? I mean, supposing in general J is sandwiched between two hidden layers, then also there is no problem, because once we know this delta Jn, okay, it is possible for us to propagate this delta Jn backwards also, right. So, the error term begins with the output, and the error term propagates from layer to layer backwards, okay. And what is the last layer up to which we have to go? We have to go up to the layer just after the input. So, in effect what we are doing in a back propagation algorithm is that there is a forward pass and there is a backward pass. Forward pass does what? It will take the inputs, okay, first compute the induced fields and the outputs at the layer just next to the input, that is to say the first hidden layer. Then from the first hidden layer it goes to the second layer. Then from the second layer it ultimately goes to the output layer. Output layer, all the outputs are available. It calculates the error terms, okay, and there the forward pass ends. We forget about the forward pass. Now the backward pass begins. We start with the error terms, okay. We calculate the local gradients, just propagate those local gradients in terms of the errors only, just propagate those local gradients into the layer next to the output, layer previous to the output, propagate it one step, one layer before that, and like that you keep on going, ultimately you reach the layer just next to the input, okay. And then everything is adjusted, all the synaptic weights, not only the ones that is connected to the output, but all the synaptic weights which are connected to the previous layers, they are all adjusted once for all. Only underlying assumption in this case is that during this time, that is to say when the forward pass and the backward pass goes on, during that time our inputs should be held steady, okay, because this computation may take some time, and if during that time the input changes, then we will be having problems. So, the underlying assumption is that during the computation of the forward pass and the backward pass, the input, the first level input must remain stationary, alright. So, that is all for today's lecture, and tomorrow we will bring in some more aspects pertaining to the back propagation algorithm, okay. Thank you very much.